Until now, we found the response of the circuit when input applied was made equal to 0. In this way, the right-hand side of the equation was equal to 0. However, it is not always necessary that the input voltage is equal to 0. It may have some other value as well. For example, a constant voltage source of 5 volt may be connected to a series RLC circuit at any time t equal to 0. Such a constant voltage source connected at time t equal to 0 to a circuit may be regarded as a step input. We now discuss a classical approach to solve differential equations when the step input is applied to the circuit. The second order differential equation with a step input is of the form this, where A2, A1, A0 and capital A are constants. The solution of such a differential equation is y of t equal to yn plus yf, where yn is the natural response of the system obtained by putting right-hand side of equation equal to 0, and yf is the forced response. We have already covered in extensive detail how to find the natural response of the system. Now we focus our attention towards finding the forced response yf. For the differential equation with a step input, the forced response yf can be found by keeping the right-hand side as it is. That is, in natural response, we've put the right-hand side of differential equation equal to 0, and while finding the forced response, we put the right-hand side of differential equation as it is. Therefore, while finding forced response, we replace y of t by yf of t and get this equation. Dividing both sides of equation by a2, we get this, which is an equation in standard form. In order to solve such an equation, where the right-hand side is equal to a constant value, we put this term, that is the term without any derivative, a over a0 over a2, yf equal to the right-hand side a over a2. Hence, the value of yf becomes a over a0. And the derivative of yf with respect to time is equal to 0 because a over a0 is a constant and derivative of a constant is 0. Similarly, the second derivative of yf with respect to time is also 0 because derivative of 0 is 0. Therefore, the forced response of the step input is equal to the value of step input divided by the coefficient along with y in original second order differential equation, this one. Instead of a step input, that is a constant voltage source applied at time t equal to 0 may be, it is possible that at time t equal to 0, an exponential source is connected with a circuit. In such a case, the differential equation may take form this, where we can see that the input on the right-hand side is an exponential 1. Dividing both sides by a2 brings it to the standard form like this. Now we apply inverse operator D method to find the forced response in case an exponential input is there on the right-hand side. In order to ease down the notation, we replace derivative by d, second derivative by d square. Therefore, the differential equation then takes this form. Dividing both sides by this term, we get y of f as this. Now, according to inverse operator D method, whenever we have an exponential in the form of n e raised to the power nt, and denominator is a function of d, we can replace d with n. Such a method is applicable if this denominator does not evaluate to 0. In case if by replacing d with n, the denominator takes the form of 0, then we need to multiply numerator by d and differentiate denominator with respect to d, and then put the value of n again. For example, when we are asked to find the forced response of this equation, we can see that there is an exponential on the right-hand side. We can apply inverse operator D method, according to which we replace second order derivative by d square, first order derivative by d, and then we can write yf as this. The formula for applying inverse operator D method is this in case of an exponential function on the right hand side. In our equation, exponential function has minus 5 in its power, so we can replace D with minus 5 here and get the solution like this. In this example, the differential equation given is this one. Again, adopting the same method, our YF becomes this. Now replacing D with minus 5, we come across with a problem that this denominator becomes 0. But yes, we know how to deal with such a situation. We multiply numerator by t and differentiate denominator with respect to d. That is, derivative of d square is 2d, derivative of 7d is 7, and derivative of 10 is 0. After taking the derivatives, we replace d with minus 5 and thus we get this solution. On simplifying, we finally get the solution of yf as minus t times e to the power minus 5t. Another example. Lots of examples for finding the forced response. If we look on the right hand side of this equation, it is 3e to the power 0. We know e to the power 0 is 1, so basically the right hand side is a constant. In case it's a constant, we know the direct method, which is right hand side divided by the coefficient of yf, means 3 divided by 12 is the answer. But now let's apply the inverse operator D method on it to find the solution. Adopting the same methodology as previous, yf becomes this. But now the power of e is 0, so replacing d with 0, we get this. On simplifying, we get the final answer as this. Yes, we got the same answer in both cases. Now that I have discussed the forced response due to step and exponential inputs, I leave the cases of ramp, parabolic, and sinusoidal inputs up to you. I expect you to search for the inverse operator D method formulas for such type of inputs and learn the way how to apply those formulas of operator D method. Maybe I would send some example solutions corresponding to these type of inputs later on as well, but that would be after you have tried for their solutions yourself as well.